So welcome back. So today we are going to discuss about types of qubits in this particular session. So so what is qubit? Before going on to that, what is qubit? So a qubit is nothing but a sort of quantum bit, which is nothing but a smallest unit of information. Okay, smallest unit of information. Okay. In normal computer, a bit can be either 0 or 1. But whereas in quantum computer, a qubit can be 0, 1 or even both together, that we call it as superposition. So mathematically we write it as ket psi is equal to alpha ket 0 plus beta ket 1. Okay, here alpha and beta are just numbers. Okay, that is nothing but complex numbers, just numbers, but decides how 0 and 1 are mixed. This is the ability to exist in both states, is what gives quantum computer the power to handle many possibilities at once. Okay, so that is the reason quantum computers are powerful. So there are not just one kind of qubit. Scientists have created qubits in many different physical forms. Some are made using natural particles like electrons or atoms, and others are made using engineered systems like circuits or tiny quantum dots. The main type include spin qubit, okay, trapped atoms and ions, photonic qubits. Photonic qubits is nothing but photons, that is nothing but we call it as light particles. Okay, and super in that we'll be having three types: polarization qubit, time qubit, and path qubit. And superconducting circuits, quantum dots, and as well as nitrogen vacancy. Okay, so each type has its own advantages and challenges and uses. Okay, but together they shape the quantum world. That is what we need to remember. Okay, so moving on to the slide 3. So spin qubits, okay, this is nothing but a tiny particle like an electron to represent information. Okay, if the spin points upward, we call it as ket 0, which this uses angular momentum, that is you need to remember. Okay, if it is pointing downward, that is 1. Okay, this is how spin qubit, I think I have given the diagram. So if it is representing upward, it is ket 1. If it is representing downward, ket 0. But when the spin tilts somewhere in between, it means it is both 0 and 1 together, which we call it as, you already know the answer, superposition. So we can flip or control the spin using magnetic or microwave fields. Okay, that you need to remember, magnetic or microwave fields. Okay, the idea is simple, but these qubits have to keep very cold. That is nothing but at low temperature we need to operate. Low temperature is required. Okay, because any magnetic noise can disturb them. That is the reason we require low temperature. So this is what I mentioned, magnetic noise can disturb. This is, we call it as cryogenic cleaning, is nothing but low temperature. So here you can visualize in the diagram. So this blue sphere represents electrons. Okay, this represent electrons. Okay, and the arrows show the spin direction. This is nothing but spin direction. Okay, up arrow means ket 0, already we have seen. Down arrow means ket 1. Okay, and when the arrow is tilted in between, let us say, it is nothing but we call it as superposition. Okay, next I'm moving on to one more important topic, that is nothing but trapped atoms and ions. This is the next type of trapped atoms and ions. Here scientists trap the single atoms. So the name itself has a trap. They will trap the single atoms, okay, or charged ions, trap the single atoms or charged ions using electric and magnetic fields. Electric and magnetic fields. Each atom has energy levels. Initially, they will be at low energy, okay. By applying these electromagnetic fields, they will move to high energy. So scientists have marked low energy as Ket 0 and high energy as Ket 1. So using these laser beams, okay, we can move the electron from one state to another, or even keep it partly in both, again forming a superposition. So these qubits are accurate and stable, but the machines need a large the machines needed are large and slow, so they are mostly used in labs, okay. And disadvantage is nothing but slow operations. So one more thing, trapped atoms and ions, the diagram itself shows. Initially it will be at 0. We are sending, or we are trapping, let us say we are trapping by using lasers or microwaves, and we are making it to move to high energy, that is nothing but Ket 1. Initially it is at Ket 0. It may lie in between also, we call it as superposition. If that is lying in between, we call it as superposition. So that is about this. Moving on to photonic qubit, I haven't mentioned because photon is nothing but a light particle, but in that we are having time qubit, path qubit and polarization qubit. Now let's talk about a different kind of qubit, the time bin or time based qubit. Here we use light, that is nothing but a photon, and encode information in its arrival time. If it is arriving early, then we call it as Ket 0. If it is arriving late, we call it as Ket 1. So we will be using beam splitter, okay, and we are making a photon to hit this beam splitter. And if it is arriving early, a photon is arriving early, for example, some photons are coming early, so we say it as Ket 0. Some are coming late, so we are marking the basis as Ket 1. So, and if it is arranged cleverly with the beam splitter, that is what I mentioned. So this type is great for long distance communication using optical fibers. So that is nothing but this will be used for quantum key distribution. I will make a video on this quantum key distribution, but it requires fast detectors and needs precise timing and synchronization. If this handling may be some some time delay or something, then will not see or will not pass the information. So that is the disadvantages. So that is why we required precise timing. So moving on to the next qubit is nothing but path qubit, okay. So path qubit is nothing but, again we'll be having beam splitter. Now again we will be sending photons. If it is hitting this beam splitter and going top, okay, we are marking it as Ket 0. If the photon coming down from beam splitter, we are calling it as Ket 1. We call it as bottom. So that is what these beam splitters do, okay, and which is nothing but it integrates easily into photonic chips. High control precision is required and requires stable alignment, okay, that is the disadvantage, and suffers from phase drift, okay, that is what you need to remember. Okay, moving on to the diagram, that is what I mentioned. It is coming and hitting the beam splitter, and if it is going topwards, we call it as Ket 0. If it is coming downwards, that is nothing but bottom path, we are marking it as Ket 1, okay. So moving on to the most important concept, superconducting circuits. So superconducting qubits are among the most popular today. So they are being used by companies like IBM, So most of the companies have been using these, and IBM and Google, okay, are working on superconducting qubits. Here a tiny loop of superconducting material carries electric current without resistance. So the electric current in the circuit, Josephson junction, we'll call it as, okay, Josephson junction. From that junction we are making current to pass without resistance. Okay, if current flows clockwise, so clockwise, anti-clockwise, okay, if the current flows clockwise, then we are calling it as ket 0. If it is anti-clockwise or counterclockwise, we are calling it as ket 1. So but because of quantum mechanics, it can actually flow both waves at a time. Okay, that is why we call it as superposition. So microwave signals are used to control and switch between these states. Okay, it is for fast gate operation, and I already mentioned it is scalable chip fabrication used by IBM and Google, but it requires near absolute zero temperature. Okay, that is nothing but 15 millikelvin. So limited long coherence time is required. Okay, I will explain coherence and decoherence in one video, in the next video. So moving on to the circuit. Okay, the loop with orange and blue arrows, okay, shows current flowing in both directions. The dual flow is the superposition state of the circuit. However, this must be kept extremely cold, almost at absolute zero, so they uh, can behave quantum mechanically. So if you see here, it is having two directions, clockwise and anti-clockwise. So already we know clockwise is nothing but ket 0 and anti-clockwise ket 1. Okay, that is what about this circuit. And you need to remember, it will pass through low resistance. Okay, current will be at low resistance, and it requires cold temperature, absolute zero, that you need to remember. So moving on to one more qubit, quantum dot. Okay, it is a tiny semiconductor particle that trap electrons. Okay, they act like artificial atoms. The electron inside the spin, it can be so the electron in the spin can be two types. It can be upward or it can be downward, which we call it as ket 0 and ket 1. So if it is upward, we call it as ket 0. If it is downward, ket 1. So we can change this state using voltage microwaves. So we can change this voltage by using microwaves and we pulses. Okay, so quantum dots are great because they are small, can be built with existing chip technology. So and they are quite fast, though they are sensitive to impurities and change charge noise. Okay, so that is the disadvantage. Okay, so now moving on to the pictorial view. So here the colored layers show the inner core and the outer shell of the quantum dot. So the correct this is nothing but, okay, outer shell, and this is nothing but quantum dot. Okay, the wavy red lines, okay, these are nothing but wavy red lines, show light being emitted. Okay, this is nothing but emitted light. Okay, emitted light when the dot switches between energy levels. So the dot switches between energy levels, the light is being emitted. That's how it processes quantum information. Okay, so moving on to one more important topic, that is nothing but nitrogen vacancy, NV centers in diamond. So what is nitrogen vacancy? You know, diamond is made of carbon atom. Okay, in lattice. Okay, what we are doing is nothing but, in place of carbon atom we are replacing, okay, an nitrogen atom. And if for example, this is how lattice looks like, let us talk. Okay, all are carbon atoms, but here instead of carbon atom I am replacing nitrogen. So what does it do is nothing but it creates a vacancy here. So here carbon atom removes, and here vacancy will be available. So this tiny defect traps an electron. This vacancy traps an electron, and that electron spin acts as qubit. Spin 0 means ket 0, spin 1 means ket 1. So the best part in this particular qubit is it works well even at room temperature. It stays stable for long time, but it is making great of for sensors and quantum experiments. So that is what, okay. But you need to know the disadvantages. It is difficult to produce identical NV centers and challenging to scale to large multiple qubit systems, okay. And this is the diagram. So if you check here, I have replaced one carbon atom with nitrogen, and it created a vacancy. In this particular vacancy I can trap an electron. So electron is having two types, spin up, okay, spin down. So this can act as superposition. So I can do my operations, okay. That is the working principles of NV centers in diamond, okay. Thank you guys. If you are having any doubt, let me know.